Hello, my name is Jesus Ramirez and I am part of the technical staff of Ocean Engineer. Today, I am going to present you the answer to one of our common questions from our customers. This is how the mass flow rate value affects the solution when we use symmetry boundary conditions in ANSYS CFX. Then, for answering this, I am going to show you a very short video with a demo that demonstrates what happens to the solution when we change or when we use the symmetry boundary conditions. Let's see it. The case shown in this video is a simple horizontal pipe flow. Then the fluid is water. Here. The fluid is water, and we have a boundary condition, an inlet boundary condition, and an outlet boundary condition. Then if you see, the inlet boundary condition is a mass flow rate, 5 kilograms per second, and the outlet is a pressure outlet with relative pressure of 0 Pascal. Then this is the full 3D geometry. Then I solve this, then I'm going to show you the results, and also I am going to show you how we did a simulation using let's say a slice of the geometry here. Then you can see that we have a slice. This is 22.5 grades. Then this is the slice. This is the angle of the slides. And in this case, I use a mass flow rate value of 0.3125. That is basically taking the 5 kilograms per second that I use for the whole geometry, for the full geometry, and I divide it by 16. That is the number of slices that we should have to get 360 grades of full geometry using this slice. And also I solve this same model but using the 5 kilograms per second. Then in total we have three cases for comparison. The first one will be the complete 3D geometry with 5 kilograms per second. The second one is this geometry, the slice geometry, with the same 5 kilograms per second. And the third one, the third case, is this geometry, but using a smaller mass flow rate, that is 0.3125. That is the 5 kilograms per second divided by 16. Then let's look at the results and see what happens to the velocity. Let us start with the result for the full geometry and 5 kilograms per second. Here we have the full geometry. Then I'm going to deselect this and I create a plane in the y-x direction. Then it shows me the velocity profile. This is a demo case. Then I just wanted to show you that the maximum velocity is 2.25 meters per second. Then we have here the boundary layer that is formed. And if we change the plane view, then if we change this to pressure, we can see that the higher pressure is around 1,300 pascals and the lower pressure is minus 3.2. Then this is what we got. Then there is a total difference between the higher value and the lower value of around, let's say, 1,301 pascals, maybe. Yep. Okay, then this is what we are getting from the full model with 5 kilograms per second. Now, let's see what happens when we have the slice geometry and using the same 5 kilograms per second. Let's look at that. Now, let's look at the result of the slide case with 5 kilograms per second. Here we can see the results for the slice case. Then you can see here, this is the slide. Let me put this here. This is the slice. Then I am coloring one of the symmetry planes. And here you can see that the maximum velocity is around 45.6 meters per second. That is pretty much larger than the velocity that we obtain with the full 3D model. Then in this case, it means that the we cannot use the same mass flow rate value when we have this kind of geometries. Let me show you. If I go here to default transfer, double click, and if I click apply reflection over the theta x plane, then we can see the whole velocity profile. Then we see the formation of the boundary layer. However, the maximum value is too high in comparison to the full 3D model. Then it means that using the same flow rate, mass flow rate value is not appropriate for getting similar results in let's say in comparison between the full 3D geometry and the slice geometry. Now let's see what happens if we use the same slice geometry, but now the mass flow rate is 5 kilogram per second divided by 16. That is the number of slices that we have for getting a fully 3D geometry. And now let's see what happens. Well, for this case, then we can see here the contour of the velocity. We have a maximum velocity of 2.99. That is pretty close to that velocity obtained for the full 3D geometry. Then if we look here into the full transfer, apply reflection over the theta x plane, then we have full contour. And we can see that this means that in this case, using the slice mass flow, let's say 5 kilogram per second divided by 16, give similar results that those obtained with the full 3D geometry. Then this means that this is the approach that we need to follow when we use this slice geometry and symmetry boundary conditions in CFX. Also, if you see the pressure behavior, you will see that the values are pretty similar to those obtained with the fully model. Then this reinforces the idea that for this kind of models, with the slice model and symmetry boundary condition, we should slice also the mass flow rate. In this case, we have 16 slices, then we needed to divide the total mass flow, that was 5 kilogram per second, by 16. Okay, now let's see that you want to see like, you know, like the whole geometry. Then a way for doing that is going here to default transfer and apply rotation over the x axis. Then now you have here what is the behavior or the let's say like a representation of the fully geometry that you can have here. Also, you can create a plane in the y zeta direction here, and you can move it right here. You have it here. You can see that, for example, you have only 12 slices. Then if you want to have a complete representation, then you go back here to the default transfer and put, let's say, this value 16. That's the number of slices that we use. And here we have the full representation of what was happening. Now let's analyze an additional case. Then we are going to use the same slice geometry with the same slice mass flow rate boundary condition, but now we are not going to use symmetric boundary conditions, but we are going to use rotational periodic boundary conditions. Let's look how this looks. Well, here we have the results for this case, and you can see that the maximum velocity is 3 meters per second. That is pretty similar or pretty near to the results that we got for the full geometry. As in the previous cases, if we want to see, for example, a reflection, we can do it from here, and we can see a plane, but also we can apply the rotation, and we can have like a rotation of the periodic boundary right? If we also see, let me do this, the pressure behavior, then we will see that the values are also similar to those obtained in the whole model. Then we can also use this approach for simplifying our model and having good results. Well, thank you for your attention. If you have any comments or any question, please contact us and we will be more than happy to answer you or to help you to solve your problems. Thank you again. Bye bye.